Mhm.
Hi, Tobias.
Hi, how are you?
Great to see you. Thanks for joining us.
Sure.
Okay, so
Okay.
welcome everyone back. Today we are very happy to have Tobias Ekholm, who's going to tell us about non-conormals, quantum curves, holomorphic disks, and quivers. Thank you very much for joining us, Tobias, and take it away.
Okay, thank you. So I'm going to speak about, oops, let's see if I can. I'm going to speak about a few subjects. So first of all, the talk is report on many joint works, and in particular joint works in progress. So it's not, especially towards the end, not completely, it's a little bit conjectural, but I hope these conjectures are interesting. But what I want to do is I first want to talk about how to count open holomorphic curves, and then they're counted in the Skein module of a Lagrangian three manifold. So I'm going to try and explain why that is and how it works and so on, and also how that leads to rather simple calculations, simple and more complete than somehow the standard calculations. And then from there on, it also tells us about somehow how these holomorphic curve counts are organized and how it seems the holomorphic curve sits. And this is in line with a lot of conjectures and guesses that has been around relating quivers to HOMFLY polynomials and so on. So I'm going to try to explain that perspective and those results, maybe a little bit more from the point of view of holomorphic curves. And I hope to get to some guesses and so on relating to HOMFLY homology and the like towards the end. Okay, but let me start with this Skein valued counts. So the geometric setup for what I'm going to tell you about is all the time a three-dimensional symplectic Calabi-Yau manifold. So that means that first Chern class is 0, and we're in a symplectic six-dimensional manifold. And in fact, it's not going to be very complicated. We're going to stick to basic things. So we'll have the complex three space, we have the cotangent bundle of S3, and we will have the resolved conifold. And then so somehow the ambient space won't be the most interesting, perhaps in this talk, but what's going to be more interesting are the Lagrangians in there. So we will have a Maslov zero Lagrangian, and the main examples are well known. So they're the toric brane. I'll draw it, you all know the picture. And then there are not conormals, and also say maybe the zero section in T star S3. So it's also interesting, but not kind of for not uncommon Lagrangian. So those are the ones. And what we're going to deal with is some kind of holomorphic curve counting and behavior holomorphic curves. And for that, we need to have an almost complex structure on our symplectic manifold. And it should be compatible with the symplectic form, means that the symplectic form is positive on J complex tangent lines. And so the holomorphic curves, they're solutions to the Cauchy-Riemann equation, meaning we have a Riemann surface, so just a topological surface with a complex structure J on it. And then we look for maps into the Calabi-Yau with boundary on our Lagrangian, such that the d bar operator on this map is equal to 0, means that the tangent space to the curve is everywhere J complex linear. So this is a partial differential equation, but it's a Fredholm equation. So it means that it has finite dimensional kernel co-kernel linearization. And in fact, you can compute by kind of famous formula, Riemann-Roch formula, can compute the expected dimension of the moduli space. And this is somehow the celebrated dimension count in dimension 3, which says the dimension is the dimension of the ambient space over complex numbers minus 3 times the Euler characteristic of the surface plus some kind of a Chern class contribution. And in our case, the Maslow zero and Calabi-Yau case kills this Chern class term, and the other term is killed since we're in complex dimension 3. So that means that one would expect the solution space to be just a zero manifold. And in fact, the way that you're all familiar with this arises in string theory is that if you do a model topological string, then the partition function localizes on holomorphic curves. So that means that somehow you have a big path integral over the space of all maps with certain fields on them of Riemann surface into your space. But in fact, the integral has contributions only from the finite dimensional subset of holomorphic curves, which in fact is 0 dimensional. Okay, so this from math point of view, this dimension count means that, well, we should be able to count these curves, and one should not be sort of too naive about it, but the moduli space is some kind of oriented 0 manifold, but maybe it's not a manifold, but rather an orbifold. So the count is maybe more rational numbers rather than integers. And this relation to the topological string tells us that if we do this counting, then what we're really computing is this topological string partition function. And if it is so, then the count should be invariant under deformations, because somehow this topological string partition function is that's the topological nature of it, should not depend on various choices and deformations and so on. And if you do the usual story, if you do the closed string story, that means that you're counting closed holomorphic curves. So you forget about the Lagrangian, you just count maps of closed Riemann surfaces, no boundaries, and so on. Then you deform the data a little bit, and the curves stay nice. But if you deform it in one parameter family, it turns out that in the closed case, the curves still stay nice because nodal curves have codimension too. So that means that if you have a double point of a curve, you want to say glue it back to an actual curve, you have a neck which has some dimension, and there is also a twist parameter in this neck. So that means that it's sort of, or if you want to say in very simple terms, it's like the equation x times y is equal epsilon, where epsilon is a complex constant, and x times y equals 0 is the nodal curve, so it's codimension 2. For open curves, these nodes, when they happen on the boundary, they have codimension 1, and the count is no longer invariant. So if you take this simple example, it's like x times y is equal to epsilon, and you force epsilon to be a real constant, right? So then epsilon equals 0 now can codimension 1. So therefore, when you deform the data and try to look at this moduli space, it's actually going to change seriously. So in this cartoon picture we see some kind of count, simplified perhaps, where we would have 2 curves, so maybe 2 disks or something like that. And what we see in this picture is we see their boundaries in the Lagrangian. And on the left-hand side, we see the 2 boundaries link. And then we start deforming the data, maybe deform the complex structure. And then what happens is that the curve starts moving, and at a certain non-generic instance, somehow this interesting instance, the curves intersect on the boundary.
Tobias,
and after that,
can you remind me actually sort of what does this mean? So you're doing this on the side after the transition, right? So not on the side where you see branes on S3, but after the transition, right? Or before?
Yeah, in some sense, yes. But this is general for any, if you have any three-dimensional Lagrangian in any Calabi-Yau. So of course for T star S3, every curve would initially be constant, so it's very hard to say anything. But as soon as you have some non-constant curves somewhere, this sort of naive counting, is not really going to work.
The reason I'm asking is maybe I'm rusty, but it seems so. If we were doing this on the side before the transition, so on the side of the S3, where then it's clear what I suppose you mean, because you know, you have these big brains that just end on the actual knots. So we're really doing something, right? But if I think about the geometry after the transition, sort of the pictures I remember is it's a little bit hard when we don't have a blackboard, but you know, this O-1 plus O-1 over P1, where, for example, a HOMFLY describes like two brains which are very far away from each other. Are they? Should I think of them still as somehow? In which sense are they linked? I suppose.
No, so it's not, so sorry. I should say that if you take, for example, the HOMFLY or unknot or something like that, you have on the brain, say, two disks forming. So you have one disk which has its boundary on the brain, and another disk which also has its boundary on the brain. So I'm drawing two such disks actually here. So for example, for unknot, right?
What I think what I'm missing is I'm missing the context of what in which we're having this discussion.
Yeah, that's right. So we're having, so if you want to go to conifold, we are having this discussion. The pictures drawn are boundaries of holomorphic curves inside the knot conormal, so inside the brain. So you have two disks, they live inside the resolved conifold, but their boundaries live on the S1 times R2, right?
Both of their boundaries live on the same.
Both, yeah, exactly. So one this U is one disk.
Oh,
its boundary is going around the S1, and the V is another disk. Its boundary is going almost parallel to it.
I see. So we're talking about transimus. Okay, I'm sorry. As I said, I'm rusty. We're talking about here transimus theory on the brain in the sort of on the pro brain somewhere far.
Yeah.
Okay.
That's right. And here we will eventually talk about U1 Chern-Simons on that brain actually.
That's right. Okay. Very good.
One brain.
That's the thing I was missing. Thank you.
Yeah, that's right. So, but what I want to say is somehow that this naive approach saying that, you know, you have two disks, you want to count them like two, well, it's not going to work because it's not going to be invariant. And the reason for this not being invariant is that as you deform the data, the two disks, the boundaries of the two disks, they can collide at some point and pass through. But when they pass through, you can also glue them up to a new, in some sense, bigger disk, right? So before this crossing, you have two disks, and after crossings, you have three disks. So somehow the count is not really invariant.
Okay, but then I'm missing still another thing, which is that before when we talked about knots in the S3, the way I was controlling the presence of these knots in the first place, like the way you put knots there in the first place, was by presence of other brains whose sort of then, you know, minimal area surfaces stretching between those other brains and the S3 would insert knots there. What am I, how do I, in going from left to right, for example, linking to unlinking, what am I varying?
Say the complex structure, if you wish. Or you're wiggling the brain a little bit by Hamiltonian perturbation.
Okay, so any perturbation that's going to do this is that.
So it's a sort of it's a very not dramatic variation. You could move the brain seriously, changing areas and so on. This is not even changing the areas. It's somehow just wiggling the complex structure a little bit, or wiggling exact, you know, make exact deformation of the Lagrangian. And so somehow the point is that we need to do something. So we cannot just somehow naively count the curves just by their Euler characteristic and something like that. So we will write formulas in a second. So we need to do something, and the solution to this problem, or a solution to this problem, is to count the curves. Instead of just counting them like that, we should count them by their boundaries in what's called the Skein module of the Lagrangian brain. So that means, in some sense, we're taking into account, as Mina is indicating, the Chern-Simons theory on the brain when we count the curves. And we will do it in two ways. So we'll do it in the HOMFLY skein, and then sometimes in the Kaufman skein, which is related to fixed points when the Lagrangian is fixed point of some involution. But we'll mainly do the HOMFLY skein. So okay. So let me tell you what this skein module is. So skein module is something that somehow came from Chern-Simons, indeed. So maybe invented a little bit independently, but in this famous Witten paper, he relates it to Chern-Simons. So if we just want first the definition, so we take a two-variable ring, and variables will be A and C, and there is a kind of famous substitution which substitutes the C for Q minus Q inverse, or with half exponents. So this is a ring, and we generate a module over this ring by taking all isotopy classes of links, actually framed links in our manifold. And then that's a huge module, but we actually divide out by the following relation. So we have the first skein relation, which is saying that somehow an overcrossing minus undercrossing is equal to Z times the resolution of the crossing. And then we have a normalization. Typically, it's somehow the value of an unknot, so that means a planar circle, is given by this A minus A inverse over Z. So this is normally introduced just as a normalization, but as we'll see, this is actually a direct consequence of our curve counting. And finally, there is this last relation that says that if you do a framing change on your knot, then that costs A or A inverse. And on the Kaufman side, it's similar. So maybe I won't detail it, but you see somehow the point is that there you have our curves have some involutions, so normalization and so on, a little bit different. But anyway, so this skein module is actually not at all hopeless to calculate. So for simple manifolds like S3, it's sort of well known that this module actually collapses, and it's just a ring itself, because by these moves you can take any knot to the unknot, and by the second condition you can replace the unknot by some kind of Laurent polynomial. So it's just a ring. If you take something like S1 times R2 that we'll work with, then you need an infinite collection of generators. So you need some knot that goes once around, some other knot that goes twice around, 3 times around, and so on. So it's actually, you need one of those in each number around knots, and then it's a free algebra, commutative algebra, countably generated by these things. So anyway, it's a rather nice object, but the most important thing of this object is that you can sort of replace some knottiness by a polynomial. Okay, and then what I'm going to try to explain is now how do we actually count curves in the skein. So normally when you count holomorphic curves, you somehow count stable maps. So what does the stable map mean? It means that, you know, when you have these curves, if you look at the moduli space of such curves, then it could have these nodal curves. So you have one curve, another curve attached to it, and so on and so forth. And the stability condition means that either your domain is stable, that means that you have just finitely many automorphism. It puts restrictions on spheres, for example. So a sphere needs to have at least 3 marked points. Otherwise, it's not stable. Or if it's not stable, this kind of component, then it needs to have positive area. And we somehow call these curves bare curves if all their components have positive area. So we'll get back to formulas where you recognize all this in a second. But what we are going to do is we are going to somehow count all the curves requiring that they have positive area, and then by hand more or less put in all these constant curves and whatever they contribute. And anybody who ever counted holomorphic curves and tried to neglect something knows that it's not so easy. So you somehow have to argue for this. It's typically you'd like to include everything and count it, and then you can get something. But we are going to restrict to these bare curves. So everything you see has some area. Okay, and then there is one important ingredient, which is some kind of auxiliary framing data. So we'll fix a vector field along our three manifold, along our Lagrangian, and then we'll take a four-dimensional chain which bounds the Lagrangian, actually bounds it twice, and it starts out like the complex structure times this vector field. So in a local model, for example, if our Lagrangian is R3, say first three coordinates, x1, x2, x3, in C3, then if the vector field is somehow x1 coordinate, then this four chain would grow out in the y1 direction and negative y1 direction. So if for example, T star S3, you can very concretely just take this graph of the vector field or whatever going out positive and negative directions. For the not conormals, it's not so hard to see that these things exist. But anyway, so you should think of this as a four-dimensional chain which goes out to infinity in these non-compact things, and the boundary of it is twice the three-dimensional Lagrangian. And we know what it looks like near the boundary. And now we can sort of
why is there a factor of 2?
I'll show you in a second. So it's very important for the that we are able to record intersections with our curve on both sides of the Lagrange. So it will appear when you sort of see that we want to trade this with a little kink in this. So it's so I go back one, and it's important for this. I don't know. Do you see my pointer? No? Yeah.
Yeah, we do.
Yeah, okay. Anyway, so it's very important. Maybe I can do this. It's very important for this kind of thing here. This relation. Oops. This relation. You absolutely need two copies of the four chain for that to hold. So it will appear in a picture in a second. I'm not really used to these things, but let's stop.
Could you remind me what this Skein module is in terms of Chern-Simons?
Yeah, so basically it is the it's the algebra of line defects in the Chern-Simons. And here, if you do Chern-Simons, the A is as usual Q to power n, right? So this is some sort of collective. It's a smart way to collect all of the line defects for any n in any, you know.
And how does
just like.
Sorry, go ahead. I was going to ask how that depends on the three manifold. You told me something about an algebra of line defects. I think that is.
It depends a lot on the. It depends a lot on the three manifold. So, so for example, for S3, which somehow is simply connected, only simply connect three manifold. This module is just the ground ring. If you take something like RP3, it's two copies of the ground ring. It's the ground ring times the empty knot or little unknot, plus the ground ring times the line, right? And in general, it's something like that. It's not known for all three manifolds and so on, but it certainly does depend on the three manifold.
Okay, yeah, sorry, I'm just confused. Like, if I think of Chern-Simons as a 3D TQFT, you can associate like a number to a three manifold, but an algebra of line defects, I would associate to something smaller dimension. Yeah.
So I didn't quite get.
If I think of Chern-Simons as a 3D TQFT, I can certainly associate a number to a closed three manifold, but I would, if you say space of line defects, I would associate that to something smaller dimensional as a TQFT. Maybe I just need to think about this, but it's not a clear construction to me. Anyway.
I mean, the basic, the starting point for this is this Witten calculation of a Wilson loop in Chern-Simons, right? So that turns out to be this HOMFLY polynomial. And now in some sense, you look at all possible Wilson loops in the manifold, right?
Okay.
And they form an algebra, sort of.
Okay, sure.
A module. Yeah.
Okay, thank you.
Okay. Okay, so so I'm going to explain to you this twice in a while, but before that, I want to explain to you that with this vector field, I can define a linking between a holomorphic curve that ends on the Lagrangian and the Lagrangian itself. So the Lagrangian is a three-dimensional object. The curve is a two-dimensional object. So I can count the intersections of this two-dimensional object with the bounding four-chain. And the key point is that in order to make sense of such a count, I need to push the curve off of the boundary of the four-chain. And I do it by this vector field. So on the picture over on the right, I have the tangent to the curve, which is independent to this reference vector field psi. And I take the normal to the plane that they span. And I shift the curve near the boundary in the direction of j times this normal. So since the four-chain goes out in j times the psi direction, the curve is now disjoint from the four-chain near the boundary, and I can count the intersections. There's no strange boundary contribution now, but I have these green points, and I call that the linking number of L and U. And now I'm ready to sort of tell you how I count a holomorphic curve. So I have to count all these connected holomorphic curves. They're all bare. And then I count them in the following way. So the first, this orange W of U is the weight. It's typically, if it was a kind of a nice embedded curve, I would count it like 1 or -1, depending on some sign. But maybe it's an orbifold, so it's some rational number. And then I encode the Euler characteristic of my curve with this Z variable. So I take Z to the minus Euler characteristic. And then I take this A variable, which is the A in the HOMFLY, and I raise it to the power of this linking number. So depending on how many times I kind of wrap around this L, I get powers of A. And finally, I take the boundary of the holomorphic curve in the three-manifold, framed by this psi vector, and I take it in the Skein, right? So all in all, I have some kind of rational number times power of C times power of A, so they're kind of elements in the ring, times whatever the boundary is in the Skein module. So I get an element in the Skein module. Okay, so this is supposed to be my count. And it's, of course, I have to count of all these connected curves. So it's a big count, typically infinite, but it's filtered by this area. So it's not too bad. Okay, and now I would like to comment a little bit on this thing. So the first, and I think it would be great if one could sort of understand some of the physics. So the math is pretty clear here, but some of the physics is not completely clear, at least not to me. So this bare curve counting is very much to do with sort of separating things with actual area from things which have zero area. So it's sort of like a separation between, I don't know, whatever instantons and perturbation stuff. So I would love to know more about how that would work in practice.
So Tobias, again, the math part. So you have this brain L in the conifold,
yeah,
which with a U1 gauge theory on it.
Mm-hmm.
So if it were in completely flat space, then the Skein module would be trivial, right? Because I think for a U1 Chern-Simons theory, there's just no braiding at all, right?
Yeah. No, there is one. I mean, U1 Chern-Simons has one thing, right? It's the framing of the knot, basically. So the A is equal to Q.
I don't think it really has. It might have framing, but there's no interaction. So there's, I mean, a framing is necessary to regulate some short distance divergence. I don't think there's any divergence in a U1 theory because it's just free. I mean, there's no
so if you have a knot, if you draw a knot diagram of a frame knot, and you want to compute its U1 HOMFLY polynomial, then you just count the number of crossings with signs and take Q to that power. It's Q to the right, which is the.
So in HOMFLY, I will be setting A to 1, right?
No, you set in A to Q.
A to Q, that's right.
So not to 1 yet, but to Q.
Okay, let's suppose that this makes sense.
No, it's basically linking number, right?
There is a self-linking number even for U1.
That's right. There's a self-linking. It's Q to this self-linking number.
There's certainly a self-linking number. That's right. That's what Maxwell had, right?
That's what Max. Yeah, this is exactly Maxwell.
Okay.
But in say in S1 times R2, it's a little bit more complicated, right? But here I could do so in this, what I'm saying here in the next little comment here, that would be like UN Chern-Simons. So you can think that you have n branes on this Lagrangian if you wish.
I see. So it's not that the things are made interesting by being in a confold, or is it?
No, we'll do transition in a second. So
so right now we're still studying just basically branes on flat space on S3.
It doesn't have to be. So here we're studying branes somewhere where there are some non-constant holomorphic curves. So more in the conifold than in T star S3. So we sort of we would like here there is some. Let's pretend there is some Cayley parameter. We have some brane in the resolved conifold. There could then form a non-constant holomorphic curve on that brane.
I'm still a little bit confused. How would you? So, in principle, right? Chern-Simons theory is the A model in cotangent space. So we could talk about Skein module. How would you understand? How would I don't know, you or Ken Fukaya explain to us what a Skein module is, just from the A model perspective? Is that what we're doing?
That's right. That's not what I'm doing, and I'm sort of saying something like the usual treatment of the A model without this 4-chain cannot explain that to us. So the usual Kenji Fukaya or me explanation needs a little bit amendment, and that's the kind of amendment that I'm trying to explain what it is. And the key player in that is somehow this 4-chain. So, and I'm trying to explain this 4-chain in the case where it's needed. So it's
going back to U1 Chern-Simons. There is of course linking number, but that's not the same as framing. Framing, the way Witten explained it in Chern-Simons' paper, comes from short distance divergences. There are no short divergences in the U1 Chern-Simons theory. The theory is just trivial.
Yeah. There is. I mean, you still need framing of the nodes, right? You cannot make sense out of the path integral without the framing on the node.
Mina, there are two framings in Chern-Simons: the free-manifold framing and the not framing. And not framing appears even in U1 case.
Yes. You need to say how how you shift it off.
I don't see why, but okay. Well,
no, because let's say you have a if you have, I mean, I don't know, but if you have one Wilson loop and you want to take it twice, you need to somehow regulate that if you want to. Just because of linking, it's like linking and self-linking is sort of the same.
Okay, so perhaps you're telling me just from Skein relations, it just follows, and let me expect that. Okay. So,
yeah. So, but what I'm telling you now is rather a story where I'm not in a cotangent bundle, but I'm in some place where I actually have some holomorphic, non-constant holomorphic curves ending on my Lagrangian. So in this old Witten paper, he has this great insight that what you should do, I mean, as you say, the A model is Chern-Simons on this brane, if you do UN, for example. And then you should, when you have this one curve ending there, you should deform the Chern-Simons by inserting a Wilson loop along this boundary of the curve, right? And what I'm saying, and what somehow is the source of this 4-chain, is that if you take that literally, like in these formulas that's on my slide here, without the little green thing, then such a thing has no chance of being topologically invariant. Because, you know, on the left, you see this almost, this is a sphere, is a disk with a small boundary. And as you deform the Lagrangian, the boundary could shrink away and it becomes a sphere and no boundary on the Lagrangian. So somehow, in order for this to be invariant, you need to encode this disappearing of a boundary circle. And that's exactly the job that the 4-chain does for us. So somehow, when it shrinks away, your sphere moves away, it still intersects the 4-chain, and by somehow putting this intersection number with certain value, you can compensate for this. So this is somehow, and what I'm going to explain, relating back to your question about whatever this A model, is that I understand in this way, in the bare curve, slightly non-perturbative setting, how to put this A back. But I actually don't quite understand how to do it in the fully perturbative setting. So that's something that needs to still be understood. And I think one has to basically put it, have some distributional area, whatever this sphere, I don't know. Okay, anyway, let me come back to to say the last word about this curve counting. So as you know, there is this kind of Gromov-Witten formula for the contribution to the Gromov-Witten invariant from a nice embedded curve of Euler characteristic chi. When you know it sits there, it's embedded, it's holomorphic. You have to account for all its multiple covers and all constant curves attached to it. And this is the formula that does that thing. But in that formula, the D here, the X is some kind of homology class. The D is the degree of the cover. And in our counts, we count the bare curves as the degree 1 part of this formula, right? So somehow we take our curves, if they're multiple cover and so on, we perturb out, so there are no multiple covers, but we keep the constants in. And then every curve should be counted as the first term in this formula. That's the nature of this bare curve counting. Okay, let me now tell you why this is invariant. And so the first thing here is kind of not so serious. One has to find some perturbation so that the bare curves are maximally transverse. They would be the 2-dimensional objects in 6-dimensional space. So their embeddings, their tangents are nowhere parallel to this vector field and so on. So that's not so hard. But what's some kind of interesting phenomenon here is that we try to define a curve count by counting only curves of positive area components. So what would kill the invariance of such a thing would be if, you know, you have a sequence, as on the left, you have a sequence of these positive area curves, which, as you deform, converges to a positive area curve with a 0 component attached, right? Such things happens all the time in Gromov-Witten theory. But what one can check, and it's somehow in ordinary complex analysis, it's of course well known that bubbling off some serious genus curve leaves a trace in the curve from where you bubbled off. So that means that the curve that you bubbled off from needs to be singular at this point, has 0 derivative, or there's a double point or some other node or whatever. And we, in some sense, we are constructing this inductively so that those curves which would be singular, well, they didn't appear in the first step. So in fact, they can be avoided in codimension 2. So this bubbling off of a constant from a bare curve is a codimension 2 phenomenon. Again, therefore, somehow our curve count has a chance to be invariant. And what it leads to is that the crossings are of standard type. So if we look at these degeneracies in 1-parameter families, then they have a standard form. So if we go on the left-hand side in the open curve counting case, there are 2 cases. One is the real node, and at this real node, we see the boundaries of the curve form a crossing, but there is also a new moduli space appearing or disappearing, which is of Euler characteristic 1 bigger. So that's the red line that ends there. And now if we sort of impose the Skein relation, so if we say that the count of the left curve minus right curve in the upper moduli space is equal to Euler characteristic parameter times the curve in the next moduli space, then as we pass this wall, the count will be invariant. Somehow we're setting the left-hand side equal to the right-hand side in this equation. And in this way, somehow this Skein relation is nothing that you just invent. It's exactly a model of how the boundaries of these Baire curves behave. So there is an elliptic version of that, which is also which related to these 4 chains. So here instead, at the bad moment, the curve has an interior point where it intersects the Lagrangian. At that point, you can open it up, and you see a little unknot. Or you can just have this family cross through. On one side, it contributes A, the other one A inverse, and that's equal to C times this unknot. So also this kind of unknot contribution is not somehow not a convention. It's actually kind of theorem in this sense. So you could if you impose it, then these wall crossings won't be crossings at all. So somehow counting in the Skein, you count something invariant. So on the left-hand side, let me not detail that, but just observe that the kind of bad moments are more or less the same. But when you have an involution for the curves, these formally ending moduli spaces of higher genus or a higher, they continue. So on the right-hand side, when you have an involution, you can make sense of an ordinary Gromov-Witten count. There are no boundaries in the moduli space. And that's kind of an upshot compared to the open count, where this was never really defined. But in the real case, it was defined, and we will make a comparison. So that's why I included. So just remember that for the real case, with the involution, there is an ordinary Gromov-Witten count, genus by genus, just invariant. Okay. And then finally, this kind of trying to.
Sorry, why do you call this the real case?
Because if L would be like the real low, so typically the involution is complex conjugation.
So you're somehow associating the Kaufman bracket to an.
Yeah. So for example, if you have if you want to do knot conormals, you take a knot, you take its conormal, you shift it up along its tangent and down along its tangent. So you have 2 copies of the conormal, one shifted up, one shifted down. And then you have the 0 section, which is invariant under complex conjugation. So now curves, if you have a curve, you can act by the involution and you get another holomorphic curve. And these pictures of the boundaries is what happens in the part of the Lagrangian which is invariant under the involution.
Actually, I am confused about something. My recollection is that the Skein relations actually do depend on framing. And that, for example, the difference between the Jones-Skein relation and the Kaufman bracket Skein relation is actually framing. So in fact, the Jones-Skein relation you get if you work in the what they call standard framing, the one defined by separate surfaces, where every knot basically has a 0 framing. Whereas the Kaufman bracket you still get from SU. In fact, Witten writes it down in his Jones polynomial paper. He writes down both. And the Kaufman bracket is the one that's actually more sort of most natural in the sense that it corresponds to the sort of simplest vertical framing. So your Skein relations depend on framing. They're not framing independent.
Yeah, I'm using the framed Skein module. So all the knots that I'm drawing are actually small bands embedded. But for the HOMFLY, my knots are oriented. For the Kaufman, they are not oriented.
No,
in terms of gauge theory, the gauge group for the
in SU2
Chern-Simons, the HOMFLY is UN, right?
whereas the other one is not UN, it's SON, right, or something. Well, what I wanted to say is Kaufman is the reason it makes sense as an unoriented theory, yet it comes from Transimus, SU2 Transimus theory, is the fact that SU2 representation is real. So there is no orientation. Yeah, SU2, yes, but somehow you can get the Jones polynomial, but you cannot get other HOMFLYs. If you take UN, right, then there is a Lev knows which groups are supposed to be there. So it's SP2N or something like that, right? It's different gauge group. Okay, so perhaps could it be that your choice of the okay, no, I don't understand. Okay, go ahead. So somehow we have chosen a framing then for all the there's some implicit choice of framing for all of your knots. Yeah. Which is like the frame. No, the framing. So I pick this vector field, and I perturb my knot so that nobody, the boundary of no, I perturb my complex structure so that the boundary of no holomorphic curve is parallel anywhere to this framing. That gives me a framing of my knot. Okay. That's how. Okay, that makes sense. Yeah. And now let's see how that also will break down in one parameter families. And here's a picture of how. So on the left-hand side, you see a moment where the knot tangent vector is tangent to our reference vector psi, right? But the holomorphic curve, where the boundary of our curve is tangent to psi. The holomorphic curve has tangent plane the complex linear combinations of psi, so it's psi and j psi. So that means that our two-dimensional object is tangent to this four-dimensional object. When I continue, you see this little green dot marked C, which is now an intersection of the four chain and my curve. And now you have to make a local check that at the positive kink, you have a positive intersection. And at the negative kink, which happens on the other side, you have a negative intersection. That's the explanation of why you need two copies of this four chain nearby in order to compensate for both positive and negative twisting. And at this moment, you're somehow trading the A variable for the four chain intersection. So there's some sort of, the real version of something disappeared. Okay. Let me make one more comment before I use this a little bit. And the one more comment is that these Skein counts are actually inductive in Euler characteristic, whereas the usual perturbative treatment is not. So in the usual perturbative treatment, I will have to deal with this bubbling off of somehow zero area curves. And when I have, for example, in this picture, I have some annulus bubbling to a positive area disk and an annulus. And now I try to forget this point on the annulus, say it came from before. Well, it's forbidden because this annulus without the point is unstable and did not appear in earlier steps. So in the perturbative story, I sort of have new boundary phenomena in each step. And it's very hard to, Skein relation is sort of like inducting on Euler characteristic. I am relating moduli spaces of high Euler characteristic to lower Euler characteristic. So I start from somewhere. In the perturbative treatment, I cannot. I have to do somehow all at once. And physically, I don't really know what that means. But it's, it's some sort of very different feature. Okay. Let me now go on and use this counting to demonstrate from this point of view this Oguru-Waffa large N duality. So,
sorry, before you start talking about knots, could I ask just to make sure I understand, is there some clear way to specialize from the Skein counts down to the original just integer counts you had before at the start of the talk?
So I'll tell you about one such specialization, but there is such a way, and the way is somehow to set this. I don't know if it's integer, but at least rational values. So you'd have to set this q equal to e to gs, so e to the genus parameter, And then this A is supposed to be the area under this transition. So the curve count in the Skein, say if you're in T star S3, will turn into an actual curve count in the resolved coniform. Provided you can kind of do away with the boundary on the not conormal.
I was hoping to not have to talk about a particular Calabi-Yau threefold. You told me about just a general story for any Calabi-Yau threefold.
And what I'm telling you is that I don't understand, and that somehow also I should have maybe said. Oh, it's not no longer there. Sorry. Yeah, it will appear later. So so I don't really understand how to specialize variables so that this becomes an honest curve count. And there is good reason for that, in the sense that, say, in this real case, when we have an actual curve count, when somehow Gromov-Witten theory makes sense, it's actually not quite the same as you know, the traditional count with GS equal this and that. It's not quite the same. And the reason is exactly this A variable. So somehow the A variable, even if it's U1, the Q coming from this 4 chain is not there. And it needs to be in order to somehow relate that. So that's a story that I don't, so that's what I'm sort of saying, that I don't fully understand how the perturbative story turns into this semi whatever, non-perturbative.
Is the issue just that this bare versus non-bare contribution? If you didn't have that difference, you would just be able to turn off some variables.
Yeah. If that's right. So somehow I can only sort of relate it to a count when I have some big area curves, and then around those it should be this substitution. But I don't really know how to get this A variable from purely perturbative data in T star S3 or T star F.
I see. Okay.
And I'll show you in an example in a second. So okay, so now I'm going to throw in some notes. And if we have a note in S3, we have a Lagrangian conormal to it, and we can take this Lagrangian conormal, we can shift it off the 0 section by pushing along its dual of its tangent vector. And then we can transition, as in this picture, we can push the Lagrangian into the resolved conifold. And in the resolved conifold, we now have kind of area of this central sphere. And this sort of famous large n duality relates the curve count on the left-hand side, which is now kind of, in some sense, ordinary curve count. I'll tell you how to interpret it, even if it has boundary on the toric brane. Here we're just writing the homology class. And the coefficients should be the HOMFLY polynomial. So I'm going to tell you how that proof would work in the present setting. So in the present setting, it works as follows, and I'm maybe restricting to curves that go once around the homology generator of LK. So I'm starting up at the right, at top right corner, and I take my conormal, I shift it off the S3 a little bit. And in that scenario, if I look at curves that go once around the generator of the homology in S1 times R2, in the LK, then it's fairly easy to see that there is exactly one curve. It's the annulus that's drawn there. On the LK, it sort of goes around the central S1, and on S3, it draws the knot, right, itself. So now we are supposed to count this curve in the Skein of S3. And of course, well, the Euler characteristic of this annulus is z to the 0, and then it's times the HOMFLY polynomial of k, right? That's what k represents in the Skein. So this is the invariant curve count. But now we can play some kind of trick called stretching. So what we do is we cut near the S3 much closer than the shift off. And then we do what's called a symplectic field theory stretching. So we stretch the complex structure there, so that in some sense you make this neck longer and longer and longer. And this is some kind of theorem that's indicated on the left-hand side of this picture, that when you do such stretching, in the limit, curves fall apart into pieces called levels. And the levels are the only way that you can go through these things is via what's called Rabe orbits. So it's some contact manifold, you have a Rabe field. And in this case of S3, it's just the lift of geodesics on S3. So in particular, if you stretch in this round metric on S3, you can calculate that the dimension input from any such closed orbit is 2 on the inside. It would be -2 on the outside. So therefore, when you stretch sufficiently long, no curve can go into the zero section. So all of them stretch away. And when they're stretched away, then we could equally well consider them as curves in the resolved conifold with some tiny, tiny little area. It's like a whatever black hole in the middle of the Andromeda galaxy or something. It doesn't matter. So these curves that we count are now the curves in the conifold, and now they're counted by, a variable becomes the homology class of the curve, how many times it wraps around the central P1, because that was the linking with the Lagrangian, which is exactly this thing. So in this process, what we would see is somehow we see this initial cylinder, it starts deforming, scaling away, and when we're done stretching, they're only closed curves, but their count is this HOMFLY polynomial. And the fact that somehow S3 is round, it doesn't have any closed, any fundamental group, allows us to stretch away everything. And so this is somehow the proof of this transition. And if you would have a more complicated manifold than S3, then certainly some pieces would get stuck in there, and then you have some contributions from things going from degree 0 Rabe orbits down to the zero section and so on. But this is sort of the mechanism, and I think it would be great to understand this thing in particular, all the levels from physical point of view, which maybe we don't. So somehow one should set up some open topological string, or not topological string theory for these with these asymptotic conditions to Rabe orbits and so on. But anyway, so this is actually a fairly, so the relation between the curve counts follows from this Skein valued curve count in pretty straightforward way. Okay, let me go on and tell you about this real curve count that we can actually do. So maybe this first picture I can skip, but the second one, it tells us that, when we had this S3 with involution, we could actually treat it like by ordinary Gromov-Witten theory. And in that ordinary theory, there is again this one cylinder, the one annulus, and it is counted like 1. There is somehow, you don't have to do any Skein, anything, the count is 1, and it's actually 1 for any knot. So you can see somehow where the difference comes from, because that count is a count in where the curves are encoded in relative homology. It's the homology T star S3 with boundary on LK union S3 somehow. And that there is no A variable there. But if we do the Skein count, then it's more like counting somehow the curves, which is an impossible task because they end on S3, right? But it's more like counting the curves in the complement of S3. And that somehow, that's not so easy to make sense out of from perturbative point of view. In this case, it works because we have some area to the curve is shifted off the conormal. They're safely of big energy, big area, and then we can stretch away, or we can introduce the A parameter without much problem. But somehow, without the A parameter, not taking this linking into account, in some sense, the count is trivial. It's somehow the same for all knots. So this is some kind of really one should understand from perturbative point of view.
Do you get some new insight into what Skein relations are for multi-covered, like for higher representations? Do you get
yes.
a new perspective on this?
Yeah, I'm actually heading there. So I'll get to this in a second. And the way that I'll get to this is is the following. So there is another sort of observation about this invariance of curve counts in the Skein, and that's that you can now actually count whenever you have some one-dimensional moduli space of holomorphic curves. If you know its boundary has to be 0 in the Skein. And so I'm going to demonstrate this phenomenon by doing a kind of now Skein-valued curve count for the toric brane in C3. So, and the main idea is the following. So on this left-hand side, so we won't have just closed curves. We have curves that are asymptotic to some Rabe chord, sorry. It's up here. And there are one-dimensional such moduli spaces. And when we take their boundary, it will turn out that the boundary consists of curves that move off to infinity in some R-invariant region, and curves that stay inside. And we want to count the curves that stay inside, the ones dimension 0 here. But if we know the curves at infinity, which is very simple, often very much more simple task, it's some finite count, then we can somehow solve for the curves inside. So let me try to carry this out for the toric brane. And I'm sort of using too much time, so I'll go slightly fast. So these are formulas for the toric brane.
Just explain things well. Don't worry about time. Just explain.
Okay, good.
Well.
So I'll explain things, but this I should not explain to you. I should explain to somebody else. But okay, I'll try my best. So here we take complex tree space, and in this complex tree space, we map it actually to real tree space by some moment maps, but I'm writing just coordinates here. So the first one is the difference of the squared absolute values of the coordinates, the first two coordinates, second and third, and finally is the imaginary part of the product of the three. So these are some sort of moment maps for circle actions. But we now take the fiber over such at some point in R3, a generic point. Then that fiber is, as this equation shows, torus times R. But if we take certain fibers and cut them down by one more equation, we get some very nice Lagrangians. So they're calibrated, so special Lagrangians, in fact. And the equations are up here, and we will actually look at this. We look at this Lagrangian L1. So it doesn't matter so much when you just take one of them, which one we take. And so that has R alpha, this first difference of coordinates 0. The other difference of coordinates squared is fixed at some value, and then we fix the real part of this product to be 0. So in this picture below, or rather maybe here it's simpler. So here's actually a parametrization of this Lagrangian. So it has two parameters. It has two circular parameters, theta and phi, and one real parameter, zeta 3. So this is an R times, this is an S1 times R2. So in the first coordinate, and I mean, you see that the surviving S1 belongs to the second coordinate. The other ones collapse somehow. And the standard picture is this picture here, where our Lagrangian is this toric diagram, and L1 is depicting our Lagrangian. It's a line going off of the plane. And in this picture, we see one holomorphic disk ending on this Lagrangian, and it's exactly the C2 plane every point of radius between 0 and R1 star. So this is sort of one basic disk ending there. It's, of course, we need to take all its multiple covers and whatnot, but it's not so hard to see that this is somehow the only disk save for multiple covers and constants. And so now we're going to try to count exactly as what Mina says. So what is the contribution of this disk? And we're going to learn that from looking at curves at infinity. So if I want to look, at this Lagrangian at infinity, I basically have to take C3 to infinity. And the other ones, I mean, R1 doesn't matter so much. when I do that. And so I have some L1 becomes asymptotic to this or invariant Lagrangian. It's just this thing. And in order to see it, it will live in the boundary of C3, which is S5. So I use the hop vibration to map it down to CP2. And when I do that, you see, I just go to homogeneous coordinates. And what I find is this torus. So it's just a product of two circles. So the last coordinate I fix, it's I. So I'm mapping into C2. And you see that the image is just a product of two tori, two circles in the coordinate planes. So that torus is Lagrangian. It's known as the Clifford Taurus. And if you look at the theta and phi, it's not just covered once, but the degree of this map is actually 2 times 2 minus 1. So it's a threefold cover of this torus. And so I know that my Lagrangian, which is the intersection of this Lagrangian with the sphere at infinity, is something that lives 3 times over this Clifford torus. And I can control the Rabe chord. So I can either do it by looking at this very round flow, or I can take the torus and deform it by some isotopy. And maybe I'll draw the picture of the deformed torus by isotopy. It looks like in this picture in the front, but without detailing that, it's some kind of technology which allows you to count holomorphic curves in such situations from flow trees. It's maybe some interesting results, but it makes it very simple. And in this case, we have 3 disks forming on this person at infinity with 1 Rabe chord. And the boundaries, so here the 2 dots here in this torus are Rabe chord endpoints. And the 3 disks, we know kind of exactly what they look like. And one is a little disk, one goes along the longitude, and one goes along the meridian. And now, so that's somehow the curves at infinity. And we now know, so I call these curves the unknot, the meridian, and the longitude. And that forms a link in my 3 manifold. It sits very far out at infinity. So somehow you have the longitude going around at infinity, you have the little guy lying at infinity, and then you have the meridian, which goes around all the way around that kind of the field S1, right?
So somehow, because you somehow deformed the symplectic structure so that these curves are holomorphic with boundaries. What did they look like in the original? Right. In the original C3, what did they look like? Like
in the original C3, so one picture of these curves is, if I draw, so maybe I'll try and draw something. So another familiar picture of this torus is this kind of moment polytope style torus, where I draw CP2 like that. And then this torus is this dot. And there are 3 disks ending on it, with 3 kind of would be Maslov 2 disks, which these ones lift, which are the lifts of those, which are these disks. So that would be the projection. But in that picture, there are also some kind of higher disks and so on. But it's exactly these 3 disks. And what I'm doing now is I'm drawing. So here I see 3 disks, and I'm drawing the boundaries of these disks on this threefold cover. Okay. So I lift them up and I see what they are. And they are, oops. And they look as in this picture. So there is one guy going around meridian, one going around longitude, and one is a little guy. Okay, so that's some kind of link at infinity in my S1 times R2. So longitude is going around S1 times point. Little guy is just like a near point at infinity, but the meridian is the S1 that goes around R2. Okay. And now, what were we saying? We're saying that these three curves plus whatever is inside must be 0 in the result in the Skein. Okay. So this gives me, I should remove my phone. So this gives me the following equation. I have a little circle minus meridian minus longitude acting on all the other curves counted in the Skein. And that has to be 0. So this is now like a Skein valued, and you'll see very explicitly in a while, it's a Skein valued recursion relation for the Skein valued curve count. And indeed, you can, there's many things known about this Skein module in S1 times R2. And in particular, these two operators have a common basis of eigenvectors, and there's one eigenvector value for each partition of the running around here. And so you can somehow just solve this equation in the Skein, and you can compute the partition function, Skein value partition function.
Explain again, why do they have to add up to 0?
So you take so there is one Rabe chord of degree 1 up there. And we're now looking at curves that go off to infinity asymptotic to that chord. And then the boundary go along the S1 times R2. That's a one-dimensional moduli space. I count all the curves in this one-dimensional moduli space. It's some kind of parametrized problem. But the boundary of that moduli space needs to be 0 in the Skein. And the boundary consists of curves moving at infinity, just moving there, and curves sitting inside still. And here in this equation, this operator are the curves moving to infinity. And the psi are the curves inside. And when I multiply them in the Skein, just take their union, that has to be 0. And now I sort of solve this equation, and I get some expression not uncommon from representation theory. So this is your formula. I mean, it's exactly your formula, but it's just formulated in terms explicitly of these line defects in the. You would get this formula if you would take, n branes on the conormal, and you write it up in this. And so this is just for making the n branes a variable. But I think that the main difference is that in this approach, there is a source for this fantastic recursion relation. The curves at infinity gives it, right? In your approach, it came from relating to the HOMFLY in S3, right? But here it's somehow, there is some kind of source for this recursion relation. Okay, so now I want to go, I want to interpret this formula, and it somehow, it gives an understanding of this quiver picture a little bit, because what we can interpret it in the following way, that it tells us if we have one of these in this red fat line, that's one embedded holomorphic disk sitting on a Lagrangian. And the thin blue line is one moving one parameter family of disks, right? This is maybe the P10. And it's telling us that the cost of crossing this big disk and all its multiple covers is exactly adding one line parallel to this disk in some sense. So even though you have a lot of complicated holomorphic curves along this basic disk, when you cross through and you add, you attach, you kind of, when you're done, the effect of it was to create one new longitude. So it tells us that even though the picture is very complicated of these disks sitting there, it's kind of captured by a very simple recursion relation. And that's the starting point for this quiver business. So before I go to quiver business, I should say that for the unknown, there is also a very simple such relation. You can write it down and find it immediately. For more complicated nodes, it's worse because of this effect that the curves at infinity, they leave some traces at degree 0 Rabe chords. So you can write up some equation of all the curves up here, but then you have to do some elimination theory that we still cannot do algorithmically in order to get to this recursion relation. But it should in principle be possible. So we're sort of working on that. But for the very simplest knots, it's really straightforward. Okay.
And Tobias, somehow you're getting information about higher representations here as well, right? This is not for one brain.
Absolutely. Yeah. So somehow this packaging things with this A in the skein on the brain is exactly packaging all representations. So any number of brains on this LK at the same time. So that's right. So it's really that's really somehow it's the non-perturbative.
I don't understand. So where's A in here?
A is in the skein of S1 times R2. So this equation.
A is Q to the n of how many brains you put on S1.
Yeah. If you would like to recover from this story, the count Q to the n, you have to set A is equal Q to the n. That's right.
But in this formula, all that would do is it would truncate the representations, which is sort of a fairly abstract thing to do. So I don't quite understand. The formula you wrote is formally with infinitely many brains.
You could say it like that. It's like, so this formula, yeah, you could say that it's for infinitely many brains, yes. It's for all the, I mean, so in fact, in this, for exactly this, if I use the standard framing, there is no A there, but if I would frame it, there would be A.
Is there an equation there, like, so I see, so it's an equation in the Skein module, and somehow there, this is a precise equation what you're writing.
Yes, this is a precise equation in the Skein module, and there is A there. And I could specialize A to Q to N, and I would get your answer. It's like the HOMFLY polynomial.
You'd get my answer with like up to n rows.
Yeah.
Okay.
Exactly.
Okay.
N times around would get, you know, that's right. Okay. So let me now move on and do the curve counts, which I think is the usual curve counts that, I mean, you're sometimes putting more brains, but when we put one brain on the Lagrangian, then we go to kind of like corresponds to U1 gauge theory, and here we would put A is equal to GS. And in that case, the Skein module will simplify and just have one variable, right? So it would be Q, the ring would depend on just one variable. And when I'm in the conifold, note that it is unfortunate, I should have two A's, but there's one A for the conormal brain, there's one A for S3. When I do this, the A for S3 is still here because it's the area of the P1, but there is no, the linking with the LK, so now A2 I set to Q. So then I get something called, I call them generalized holomorphic curves, but it's really counting in the U1 skein of the LK. But those are, they should behave as the ordinary holomorphic curves that we normally deal with. So for example, I can take the skein and I can project them to homology and then take Q to the linking, and that survives, it's still invariant. So in particular, when I do this recursion relation for the toric brain, it will now have this familiar form that I take e to the x minus e to the p, 1 minus that, so that this is the unknown 1 minus longitude minus meridian acting on the wave function is 0. And if I solve it, I get this very expression, you know, of the quantum dilogarithm. For the unknown, I have some other solution, but let's focus on this. Let's focus on this thing here. So I will now take this to, so here's some example. Let me, it's the trefoil, but let me note is somehow this recursion relation for the trefoil more complicated, but let me not dwell on that. So what I want to do now is I want to go to the other side and see from the inside where might this nice finite recursion relation come from. And there was some observation about HOMFLY polynomials that you can actually write them, the colored HOMFLY polynomial, as a quiver partition function. And I would like to explain that there is some kind of holomorphic curve geometry behind such expressions. And the basic intuition is the following, that if you have a Lagrangian somewhere, then a neighborhood of these Lagrangian looks like cotangent bundle. And now, and you can maybe do like whatever, U1 Chern-Simons or something like that in there. But now you can think of these Lagrangian deformed by attaching one holomorphic disk to it, right? And what does it mean deform? It means that I allow holomorphic disks, I allow holomorphic curve lying in T star L union this blue thing, right? And then we would have something akin to this Witten picture that I had before, right? We just have to, we can abstractly attach such disk. Okay. And in fact, you see, I should go back. We basically, for this toric brane, we basically figured out whatever holomorphic curves there are inside here and their boundaries and, you know, genus and so on. So now if we have several such disks attached, we just need to see how do they combine in this U1 skein. And the answer is that they combine by the linking number. So if we take a matrix Cij, and the Cij is the mutual linking number between copy disk number I and disk number j. Then we can just compute what is the contribution to the total curve count. And the contribution is this second, so I'm now at the second line in the equation, and that's somehow this quiver partition function. So basically this product takes all the multiple covers and constant attached, and then we see the first factor here, see how they link, and that gives us somehow this U1 Chern-Simons contribution or the contribution in the U1 skein. So the first line is actually an interesting observation, that if you write it up, so you take coordinates, which is somehow e to the x1, e to the xm for the various disks, and you introduce a dual variable of it, which I write as e to the gs ddx, then you can write the partition function as just a product, a standard product of quantum logarithms in non-commutative variables. So
are you somehow using your Skein module to pull the knot apart into just a bunch of unknots?
You could, it's going to there, but the only thing I'm saying now is that I have, if I have a Lagrangian, which is deformed by attaching some number, finite number of disks in some way, and I know the linking of those, I can write down the corresponding partition function.
Sure.
And that's a quiver partition function. And I'm observing that that quiver partition function is actually just a product of quantum logarithms if I write it in some slightly strange variables, and then normal order, okay? So, but maybe the upshot of what we're doing is that we now have some kind of geometric understanding of what the quiver variables are and what the linking is. Sorry, what the quiver matrix is. The quiver matrix is the linking between the disks, and the diagonal things are the self-linking, and then somehow if you look at this e to xi, there is an e to lix, that's how many times it wraps around the S1 in the S1 times R2. There is an A, which is how many times it wraps around the CP1, and then there is the most interesting Q to something, and that are basically the 4-chain intersections of the disks. The intersection of the disk with the 4-chain of the LK. Okay, so now here's the well-known. We would like to say, and I will come to that conjecture in the end, but there's some conjecture that for every knot, if you take any knot conormal, there is some kind of finite number of disks, so that the partition function is the quiver partition function. For the unknot, well, we all know and love these two disks, so they're the blue and the red one in this picture. There are two disks, and they explain.
So again, I thought that you're going to try to. Do you think it's feasible to try to explain how these quivers arise?
I hope, but I'll tell you more. So it's a few slides away, but I hope to tell you. Okay, so indeed there's a lot of experiments here. So the unknot, you have this little quiver. For the trefoil, you have a quiver with 6 nodes, and the linking and self-linkings are somehow indicated in the picture by green lines and whatever the other color is. So it's a little bit complicated.
And this is supposed to capture all representations?
Yes. Well, at least all symmetric representations. So let's see. All symmetric. Yeah. Let me at least maybe more in the end. But okay, I'll go.
Actually, is there a structure there that okay.
Yeah. There will be a fantastic conjecture towards the end. I'll give you some structure. So, but before structure, there is this thing that you asked about earlier. So, in fact, the first question one could ask somehow, if you have this quiver and you have a partition function, is it that the partition function is uniquely determines the quiver? And the answer is no. And there are some kind of natural moves on these quivers, which seem to be somehow the only sources for non-uniqueness. It gives a huge collection of quivers that have the same partition function, but it seems like there's some kind of thing like this. So the first thing is there could be a canceling pair. So if you have 2 disks which have the same A and this is the same A and the same X power, but they differ from each other so that one has a self arrow and the Q inverse, a 4-chain intersection. Then, in fact, if you do the partition function, you see that they cancel. So you can add this pair to any quiver, and as long as both of them link, with the same number to everybody else, there's no change in partition function. And then there is this somehow the thing we started the story with, which I call multi-cover Skein. So it's exactly this first crossing. You have, I don't know, on one side I have 3, it seems 3 disks, another side I have, maybe it's 2, one is fat disk, I don't know. And anyway, 2 goes to 3, and linking behave as linking kind of should. So you see you have a 2-node quiver, you cross through, and you reduce the linking between them. It should probably be K here, but by 1 at the expense of creating a new disk. And so it's also under this move, the quiver partition function is unchanged. And so it's somehow interesting because we are doing this Skein move now, basically carrying all the multiple covers and constants attached. And the interesting piece is that if you would take a basic curve, an embedded curve, which is not the disk, so for example, annulus or something like that, and you try to prove this crossing formula, it's simply not true. So it's some kind of important thing that is important for the quiver picture, but in general important that if you have like an annulus and you would like to cross, the first thing you have to degenerate the annulus to some disk or 2 disks or whatever, then you can cross, then can go back and see what it is. So it's really important that these things are disks. So when you have this wall crossing or non-wall crossing, whatever it is, I don't know, you first have to go to subdivide the curves into disks, and then you can do such crossings. Finally, there's also a framing change, which actually changes the partition function, but in some kind of controlled way. Okay. So what we have right now is maybe for many knots, we can check we have a quiver. It's far from unique. We can somehow generate very many quivers. So one would like to have some control of this thing. But before control, I want to say that when you have these quiver forms, actually there is always a recursion relation which looks more or less like the toric brane. So the key here is to use the right variables. So if you have, so here I have a collection of quiver variables, this xi, and I introduce dual variables yi. I think I dropped exponentiation here for some not very pedagogical reason. I'm sorry, but so yi acting on xi is q squared xi and yi on the other side. So it's commutation like that. So I can first do some kind of unlinking. So if I introduce new variables, I take my xi and then basically multiply them by all the yi's to their linking powers. That means that I have new kind of quiver variables which now commute. And then I can mess a little bit more with them. So I take these commuting quiver variables and I multiply by all the duals of those which have a larger number. I have to number them somehow, and I multiply those which have a larger number. So it basically means that if I think of them as strands, I have first parallel strands, and let the second strand go around the first one, the third one go around second and first one, and so on. So some kind of nested linking. Okay, if I do that, and then introduce this variable c, which is the sum of all the variables, well, I can write c to power r, expanding it out by kind of Q binomial theorem. And then I get exactly if I take exactly the expression for the partition function for the toric brane in variable c, it's somehow from this previous formula easy to check that when I normal order this out, I get exactly the quiver partition function. And then see what happens is that since zr is equal to c times zr inverse, zr minus 1, we have this kind of recursion formula in these strange variables. So it's just the exactly toric brane recursion formula. So sometimes I want to skip this. Sometimes basically these go more around. You have a more complicated recursion, but still not so complicated. So of course, when you want to write the recursion relation in the usual variable y and x, it's a lot of stuff to do. But it's somehow the fact that in this quiver world, and for all of these basic holomorphic disks and so on, it looks like all recursion relation basically look like the same recursion relation. So I don't know very well wherever this structure come from, but I think it's sort of interesting observation. Okay, so let me now go on to a more speculative thing, but maybe ending with this conjecture about what the quivers should look like and where they should come.
Have you shown this to people like Eugene Kucharski?
What was that?
Have you shown it to people like who do representation theory?
Yeah.
My feeling is that this is not that new. That there's
probably not. I mean, it should not be. I think it's some probably not. But I think it's sort of important. In particular, this form of it is important because it would catch some pieces for nodes which do not have all the kind of quiver nodes going once around. This formula should leave some trace. I think the 942 is the first one. Anyway, let me now kind of go on to this. The quiver story that also has some kind of refined story, which is not equally well understood. So if you have a quiver, you can define a refined partition function. And I'm just giving you the definition is as before, but we introduce a new t variable and take it to the self-linking. There is a kind of physical reasoning, if it was basic holomorphic disk, why this should be the case. It's a kind of mimicking what you did and making a topological twist. But what the observation is that there is some kind of simplest or best quiver for at least simple nodes where it's been tested, for which this refined partition function knows the colored HOMFLY homology, and at least in the symmetric coloring. And the way that it's supposed to go is that you take this function and you express it in terms of kind of standard Pochhammer symbol. So somehow it's like an equivariant point, equivariant vortex of vorticity n. So that you expand it in that, you get some integer number, and those should be the generators of this homology. But And then, so in this, of course, it's a kind of inspired by many people. And from there, so we're somehow, it seems that this refined function knows the HOMFLY homology, and there should be a differential giving the SLN homologies. Let me maybe not detail that, but come to this last structural theorem. So here is somehow some kind of conjecture in line with Nina's question. So I'm maybe explaining it here for the nodes which have just once around generators. You have to modify it a little bit, but not much for the many times around. So the idea is that any such node should have a quiver of the following form. So you have the quiver nodes come in pairs of pairs. So the first pair is somehow going from reduced to unreduced. And so instead of taking all of them, we can take kind of half of them.
So reduced, unreduced what?
It's like reduced and unreduced HOMFLY. So for the unknot, we had 2 nodes, right? In this representation, we will start from 1 node. And the way that we are creating the pairs is by taking this 1 node, and we take a small circle of which you think of as a sphere, which just links all the little disks, right? So for the unknot, we would have 1 disk, and we have a little red guy which links it. It's just it doesn't go around the X1. It's like an opened up CP1. And when I cross through, I do the quiver move. I get now 2 disks, one which is a kind of with the twist and an A squared in. And that's the unknot. That's the unknot pair. And the other thing that we know about all these quivers is that when you take the SL1 homology reduced, you get just 1. There's just one one-dimensional space. So everybody else have to come in SL1 pairs. And in examples, at least, it looks like there is another little disk which has A squared Q minus 2 in it. And it links with everybody except 1. When you push it through, you get another quiver. And that somehow that should be the form of the quiver for any node. And in this form, it is completely unique. So for the trefoil, for example, we have this 6-node quiver, but this alongside this conjecture, it would be like there are 2 really important nodes, and then there is a red one which links both of them. And if you want to go back to this quiver, you cross it. You create first 2 nodes here and 2 nodes here, and then you have the blue one linking those 2, and you double both of them, you get the 6-node quiver. So somehow there should be a basic node, which is the one that survives in SL1 homology, and then there should be pairs of nodes which are canceled by SL1 differential, and we don't really have any direct way of reading this off and so on, but where it should come from geometrically is the following, that I believe you take this conormal of the knot, and you can put it like almost like a multiple cover of the unknot conormal, right? You braid the knot around the unknot, the conormal lies very close. You degenerate it onto the conormal, and you push the conormal down right to the vertex in the coniform. So now everything is very degenerate. The holomorphic disks basically have to converge 2 copies of the central sphere and maybe the constant disk sitting at the vertex. And that's exactly somehow this picture. So I haven't tried very hard, but I hope that it's not impossible to actually reconstruct the data of the basic disk from a link diagram. I don't know how to yet, but I think for trefoil you could do it and so on, but in general I don't know how to do it. But I believe that this picture should arise from that very degenerate limit where all the holomorphic curves converge to very known pieces, and the main point now is we should understand how to open them up to give these basic disks. And yeah, I don't, except maybe for trefoil. Okay, that's where it is, right? Okay, I think I'll maybe stop at this. I talked too much already. Take questions.
Thank you, Tobias.
Thank you.
But so your understanding of skeins on brains does not help kind of give a derivation of these things. It does.
These things, no. No, I think what it helps, it doesn't. So in some sense, skeins on brains is telling us there is some invariant curve count, and it's basically so this quiver business is a much deeper story in the sense that you remember, maybe I can go back. So there is this somehow. Oh.
I guess the issue is that a quiver knows about all symmetric representations, and your schemes know about only about the fundamental or one representation. Yeah.
So in some sense, this Gukov formula, it's not quite like, it's not exactly like that, but you know, in this Gukov formula for holomorphic curves, the skeins on brains is some way of perturbing out, and then you can use just the first term of this formula. So if you have one basic disk, what you would have to do is you would have to perturb out so that all its multiple covers are no longer multiple covers, they're embedded curves, and then you automatically take care of the attaching of constants. But the quiver picture is on pair with the Gukov formula. It's taking all the multiple covers, everything at once, right? So it's somehow perturbing even less. So you see what I'm saying? So skeins on brains is the first term in this formula. The quiver picture is all of it.
At the same time, you would have thought that basically a node of the quiver somehow comes from a single disk plus its multi-covers. So once
exactly,
you
yes,
disk, you know everything.
Yeah, that's right. So that's exactly. But the skeins on brains deals with the node after perturbing all the multiple covers, but not the constants in some sense. So the skeins on brains tells you at least we have some kind of partition function which is invariant, but it doesn't help more than that.
I mean, to be honest, I don't think that this quiver story is interesting unless you actually have, you know, some systematic way of deriving it. Knot theory is a very, in some sense, dangerous business, right? Because it's so beautiful and it's so, you know, there's so much structure in it. There's many ways of sort of, you know, thinking you're finding something nice where you're just like finding some small pieces. So unless you have a way of explanation, it's just, you know, one of the many miraculous things that happen in knot theory. But
of course, I mean,
but because the formula, as you explained, right, for the quiver, it just involves the linking number. It involves sort of very little data. I would hope that you somehow have ways of, all you need to do is somehow figure out how many components and, you know, what are the links.
Yeah. I mean, for simple nodes, for simple nodes, you can basically always do it. You look at the HOMFLY polynomial.
No. Can you do it from the geometry? Of course, you can do it from the answer, but can you do it from geometry?
Yeah, that's what I'm hoping. So for trefoil, I can do it from geometry. In general, I cannot so far. But the hope is that, you know, I don't know exactly how to catch it before the transition, which would be the best. But at least what sort of makes you hopeful is that when you degenerate the conormal to a multiple of this unknown conormal, you know that all the disks, the basic disk, has to go to combinations of disks on the unknown, right? So the main thing is you need to figure out how you recombine them into actual such disks on the LK. And we're not there yet, but at least
maybe Lev can tell us if there's a way of there's a hope of approaching the problem that way, because he knows everything about that way of thinking about things. Maybe he's not here.
Yeah, he's here. But...
I'm sorry. Did you mention me?
Yeah, I was wondering whether your story...
Okay, let me make a comment. Maybe I did not quite understand the business with the Skein modules, but I thought about quivers some time ago. Maybe this is already known. So my feeling is that a natural way to get to them is to use D2s instead of string instantons. So I would compactify the Taub-NUT, and then I would try to put the conormals in a position which is in a sense opposite to what Vafa, Oguri, and Labastida Marinho were wanted. Namely, instead of having smooth curves, I would put conormals in such a way that D2s will have the form of disks which intersect each other. So make those curves very nodal.
Yeah.
And then accounting for the, so then you have to deal with a stack of disks of D2 nature, which is relatively simple, I think, although I think it will be D2s with the A twist. I'm not very familiar. And the intersection will be some common line defect, kind of a double. You will have a Toft line in one stack and paired Toft line in the other stack. And that is what would create the quiver. So I guess the stacks of disks will be the nodes of your quiver, and the common points will be the arrows. And again, I think that working with D2s is much simpler than counting curves Gromov-Witten style.
Yeah, this in some sense what I'm saying. I think it's not far from what you're saying. This degenerate conormal puts the D2s in that position, and indeed, I mean, these quiver nodes, they are sort of before. I mean, they are encoding Gromov-Witten, but you deal with them, as you're saying, as with D2s or even maybe even M2s. I don't know. But,
yeah. So they originate from M2. I'm sorry, I interrupted. So yes, they originate from M2s. The question is whether you turn them into D2s or into string world sheets.
No, I think I
suggest that, and I suggest to use D2s because it will make the calculation, I think, much simpler.
Yeah, I agree.
The second comment is that perhaps. So what you were saying about multiple covers is very similar to what we had in mind with Alexei, and we're writing this up. It's a long procedure with Tudor Demoft. So the idea is that you can put conormals on the resolved conifold side in a special position, in which, in fact, all D2s will be close to a single stack of disks. So it will be a single stack of disks which ends on a braid, on a very tight braid.
Yep.
And they all sit in, and this stack of D2s sits in the fibers of one of O-1s over the north pole of P1. So I can comment more on that. So,
So you even, I see.
So in this situation, I think you will have a lot of control over the way that you will get individual disks intersecting with each other by looking at how the strands of the braid go around. So again, I can give you more details on this.
Sure.
So I think that this would be the way to see.
I think this is not far from this this z variable that I introduced. I think the z variable is this. The thing, the very heavy person that you're talking about, all these disks in some sense. The z parameterizes your heavy person, where everybody sits inside. I think that's the case. But yeah, I don't know. Yeah, so indeed, so far I don't know exactly how to get this quiver partition. I mean the quiver from a knot, but I believe, I mean exactly how I don't know, but I think you have to degenerate it either some way you're saying, or maybe degenerate the conormal. And I think it's not. I think it's not impossible actually.
So I think that the braid approach, I think gives you a lot of control over the geometry, because if you have some general conormal somewhere in the conical.
No, that doesn't do it somehow. And I think, yeah.
I mean, the picture you drew with these sort of operators, right? Stacking up sort of unknots, right?
Yeah.
Or alternatively, with this braid approach, right? It has an advantage. It has a disadvantage, which you may be able to turn into an advantage, which is that there's many different ways of presenting a trefoil as a braid. Most extremely inefficient ones. So if you thought about the inefficient ones, you might figure out.
Yeah, that's right. How
what it is that. Well, what's the that way you can keep thinking about one knot, which you understand fairly well, like the trefoil, while trying to present it in more complicated ways and figure out what's the systematics of the translation between the braid and the answer that's supposed to be the same at the end of the day, even though not in its pieces.
I agree. I think that what is somehow the addition of this story so far is also that there is a kind of there is an understanding of this recursion relation directly, right? So if you look at these curves at infinity, for simple knots you get directly. For more or less simple knots you need to do some kind of elimination theory, but it's obvious in this business that thing is just a polynomial. I mean, it's a finite differential equation.
That relation you're writing is amazing, because I certainly didn't know that such a thing exists that would capture all representations simultaneously, and your thing does. And if you put more brains, if you go
But
and
this is just, I mean, this thing in general will be just a recursion relation for the symmetrically colored HOMFLY, right? And but this recursion relation now has a geometric origin, and so what I think would be, and somehow math-wise we know some of this theory, but physics-wise I don't know what lives at infinity on the brane on this resolved conifold.
Say this again.
So if you take, I mean, take any knot conormal or take a just toric brane if you wish. So what we're saying is that there is some kind of theory out at infinity of this toric brane, where the brane just looks like T2 times R. And there is some kind of curve counting out there with this Rabe chord asymptotics. And the question is, what is that theory in the physics?
No, I mean, we in principle, we know everything about that theory. It's exactly what I mean, in some sense, Witten's paper on the A model told you what that theory is. It's U1 Chern-Simons, which could be a little exotic because U1 theories are actually in string theory they're much more subtle than higher end. But anyway, so it's a U1 Chern-Simons plus whichever disks your geometry provides, and you have to put them in by hand, and that's the theory.
Yeah, but these disks now are not closed, so they have asymptotics at Rabe orbits, Rabe chords, right? So
yeah,
I mean,
I think that, yeah.
So it's a kind of relative.
So in Witten's story, there would be holomorphic disks.
Yeah, these are also
holomorphic. Disks exist because you're choosing some crazy symplectic structure, which
no. But there's nothing crazy about this symplectic structure. They exist in C3 at infinity.
But how can they? Okay.
Because they exist because you have positive asymptotics, right? So it's like they blow up somewhere, but they blow up in a controlled way that they're asymptotic to some kind of chord there. And so those punctured holomorphic disks, you know.
So, well, okay, so if they exist, you have to put them in two.
Yeah.
And that's the data of the theory.
That's the data of the theory, but that theory and that theory that you get out there is somehow much more finite than the theory you have inside. There are no multiple covers for free because you have this one Rave orbit. So all the disks are nice and not multiple covered.
Wait,
and so
I
on.
would still have to. You cannot get rid of your multiple cover, the one that comes from the inside. I mean,
no, the
unless
ones that inside they're multiple covered, but the ones that leave out there, they have one positive puncture. If they would have two positive punctures, they would have dimension 2. So in order for them to be rigid, it's just the disks that you see or curves you see, plus some constants on them for free. So it's a kind of a.
But there are also disks with no punctures. The one that just comes.
Yeah,
from,
but they always far away inside.
Yeah, that's right.
And then those are somehow described nicely by this deformed Chern-Simons and so on.
Yeah.
And these ones should also be, but it's in some kind of other version Chern-Simons, right? In some kind of R invariant story, and so basically from
I mean, Witten's prescription is right. Chern-Simons theory is everything that can sort of shrink to graphs, and everything that your geometry provides that cannot shrink to graphs, you have to add in, and figure, and that sort of inserts operators in your theory, and that's that.
Yes, but that's right. But in this. So in this theory, whatever it is, at infinity, there is a kind of there is an unusually finite operator, right? And somehow it gives you, in an unusual way, a finite length equation that has to be satisfied.
Can you try one more time to explain the geometry of this? So you.
Yeah.
Yeah.
So okay, so I'll take this picture over here. So we have some Lagrangian sitting inside a, let's say, resolved conifold. And at infinity, so say this is at infinity, resolved conifold looks like unit cotangent bundle of S3. And let's take this to be a not conormal. So at infinity, this not conormal looks like the unit conormal of the knot, right?
Mm-hmm.
Sitting inside there. So it's a 2-dimensional torus in a 5-dimensional space.
Mm-hmm.
And when we multiply this thing by R,
Mm-hmm.
At infinity, things become R invariant. And so we can have holomorphic curves which have punctures at infinity where they go to these Rave orbits, Rave chords. So this is a chord, basically, at infinity there are these chords which connect the boundary of L to itself. In geometrically, they correspond to some geodesic meeting the knot at right angles, but they're really far out at infinity. So it has a puncture there, and then it goes in along the R times dl, right?
Okay.
And those curves which already moved into this R invariant region, they together with all the rigid curves inside form the boundary of a 1-dimensional moduli space of curves.
Mm-hmm.
If you want to see this moduli space, you take a curve out at infinity, you start pushing it in, and it will move in, maybe it intersects the rigid curve, picks somebody up, and then it goes back up and disappears. And now, because we have a 1-dimensional moduli space of curves, its boundary has to be 0 when we count it. Its boundary is 0 in the Skein. And so we know that the curves at infinity plus the curves inside, I mean, this joint union is 0 in the Skein.
Yeah.
And what happens is that the curves at infinity, I mean, inside, whenever you see anything, you see kind of a myriad of curves, right? But out at infinity, that's not the case. You basically have some finitely many curves. So for unknot conormal, it's 4 of them. For the historic range, 3 of them. For other things, it's some finite number. And this finiteness gives you a finite operator acting on this thing equals 0.
This is, I mean, it's magical. I understand. It's beautiful.
It's nice.
And okay.
And at least it may be useful to show that somehow, you know, if you want to find these quivers, they need to be finite number of disks or something. Could be finite number of disks. It's somehow related to this. So this would be some kind of backtracking way of getting at the disks. It's not also not there, but it's not impossible.
The equation you wrote is so magical. I've never seen anything like that. I've seen quivers, you know, they appear in so many contexts. So that to me is much less exciting than the equation you wrote down. I would just follow it because it's the most powerful equation I've ever written in this business.
Yeah, this is
the fact that you have it, I would just, you know, see how far you can push that story. That's magical stuff.
That's right. So the other thing, of course, I mean, what one should, or I mean, that should also be said. So this is also not I don't know how to do it, but you could imagine following what you did in this refined story. And if you could, you know, if you could upgrade this equation to the refined version, and then you're done.
I don't think a model should know about refinement. That's
no. Of course, you need to put more, right? You need to put more. But the question is, if this symmetry, the symmetry that comes from this S1 action on S1 times R2, if that can be read off at infinity, I don't know. But if it can, you have some chance.
Can you? Maybe you said this probably. Can you write down analogous equations for other okay, you wrote it for conormal in S3. How about for other knots? For conormal.
Yeah. So okay. So what can we do? We can do unknot HOMFLY. So we're working on writing some kind of algorithm. So the point is that you need. So what we can do, hopefully, is that at least we can write the equation before elimination theory. So we can write all the relevant curves in the Skein, and then one has to solve the equation somehow. And that should be done. So that should be like what we did for this knot contact homology. So given a braid representation of a knot, it's a good hope that you can write the counterpart of this recursion relation, but with a few extra variables that needs to be eliminated. And of course, better than that, you cannot do. The question is it, you know, realistic to have some systematic procedure for this elimination? And I think it is, because somehow the elimination, how to say, we kind of know how elimination works, how this works in semi-classical approximation. And when you have this Skein or more quantum picture, the elimination theory has to follow very closely semi-classical pictures. So I think guided by that, you can do something. But okay, we're not there yet, but this is sort of first step. I think, I mean,
it seems to me
I think Lenny can do
the story is. It's
huh? What was that? Say again.
Seems to me that's sort of where the real meat of your story is. I mean, this is really, yeah.
No, that's right. So this is really important. That's right.
Okay, great.
Yeah.
Okay.
But, yeah. No, but the rest is I mean, I think you have to degenerate in order to get this quiver or whatever directly. You'd have to degenerate somehow. I don't know exactly how, but I think Lev's suggestions are very interesting. But I agree with you. One would like to know, how to do it.
No, I mean, maybe some really clean systematic story comes out, and then it's wonderful.
Yeah.
But this is
but I think also it's some kind of I mean it would be nice to also see somehow maybe to you it's already kind of clear, but to see these sort of not homologies as these PPS things with tunneling when you have certain parameters and so on. I think this would be a very nice picture. But we'll see. Yeah.
great.
Okay.
Thank you so much, Tobias.
Thank you.
It's late where you are, right?
Yeah,
Okay.
it's a little bit late. But
All right. Thanks for joining us.
Yeah, sure. Thank you very much.
All right. Take care.
Yeah.
Bye-bye.